Connor Manning, and I'm here to talk to you about trillions of points and the organization of massive point clouds as infrastructure. So first, briefly, many of you may know, but what is a point cloud? So it's a collection of 3D spatial points. So at minimum, there's an X, Y, Z, and there also may be another of other attributes like intensities, RGB coloring, classifications, GPS times, things like that. Here's kind of a close-up shot to show you all these individual records and also to kind of differentiate the fundamental of what makes a point cloud different than something like a raster product. So like here we're looking under a bridge. So as you can imagine with data like this, the magnitudes of the data sets can get quite large. So I have just some examples so you can wrap your head around it. So for example, to take the entirety of all the US interstates with terrestrial scans, so via cars driving around, would be about 15 terabytes of data uncompressed. For all of the USA, for airplane scannings, that would be about 1.5 petabytes of uncompressed data. And with the best compression for point clouds getting you 6 or 8 to 1 or so, you're still looking at hundreds of terabytes of compressed data. And these data are typically organized as tiles, and lots of them. So each individual color there, which is quite hard to see, so I'll go to a closer up shot. Each of these is a separate file, so they're organized spatially in a spatially distinct way. And they tend to be a little bit large, so I don't know if you can read that, but each of these colored tiles here is about 40 megabytes of compressed data. So that decompresses to approximately 200 megabytes for each one of these little tiles. So it can be a little bit difficult to work with because tiles are problematic in a number of ways. For one, it's physically difficult in that a prerequisite for doing anything with the data is downloading one or a handful of these tiles. And it's also logically difficult because once you've done so, you've isolated yourself in a little section and you can't really treat the entire data set for something like, say, the Netherlands, which we just looked at, as a single logical unit. And it's also pretty much impossible to visualize. All you can really do is download the data and maybe look at those little patches individually. So spatial indexing is the reorganization of the data in some way. There are a variety of ways to do it. A common one is an octree. This is kind of a demonstration of what an octree looks like in practice. So it's kind of like a Rubik's Cube type thing that subdivides into higher resolution Rubik's Cubes recursively and so on. So as the point density slider moves around, you can see the higher resolution pieces filling in and coming out. So what I'm here to talk to you about are two projects called Entwine and Greyhound. Now, Entwine, I'll go over pretty briefly. It's the spatial indexing piece, so it's the thing that actually builds these octrees. And it's built atop of the Poodle or PDAL open source point cloud library, which point cloud people are probably at least familiar with. Has a pretty simple API, but and it's also cloud aware, so you can use S3 or Google Cloud Storage, stuff like that, or just your own computer. But most of what I'm going to talk about today is Greyhound, which is a server piece that sits on top of these Entwine built spatial indexes, and it is an HTTP server that allows you to drive spatial queries. So together, these two products provide a web services solution to the data management of these really large-scale point cloud collections. And some of their philosophical points are that they are engineered to be lossless, so they never discard points, they don't mutate data, they maintain all metadata. So theoretically, you could reconstruct that set of tiles from the spatial index, so you can put the original set in cold storage if you so please. They're cloud scalable, which I kind of mentioned, so we've done some parallel processing on like 30 of Amazon's largest EC2 instances, which is kind of cool. And they're built with a visualization first mindset. So we want to be able to visualize things. And I'll come to that point a little bit later. So the core API of Greyhound is pretty simple. There's a couple more calls than this, but this is the core piece. So you can get info, get metadata about this large collection. You can learn about the original files that went into the collection. And the main one that gets used the most, of course, is read, which actually reads your data. So I'll briefly talk about what a read query looks like. It looks kind of like this. So you give it some bounds. You can give it depth ranges within the octree. You can do scaling and offsetting. You can pass which attributes you'd like. If you're a renderer, you probably don't care about a lot of them. You only care about maybe XYZ and RGB. If you're doing exploitation of the point cloud, you might care about more than that. You can do arbitrary filtering with a syntax that probably a lot of the JavaScript-y people here are familiar with. So this is a straight replica of like a MongoDB syntax. So you can apply arbitrary filters based on the values in these attributes, and they can get quite complex. We won't talk about that too much. And one of the main things that these products can do is they provide a visualization mechanism. So you can put trillions of points in your browser, and down there at the bottom are 2 screenshots of some open source renderers. Some of you may be familiar with Poetry and Plasio. So I have a little video. So this is Poetry browsing around some of our larger data sets. So this is Denmark. You can see it doesn't have good color throughout the whole thing. And we have the Netherlands down there. So already we're looking at 2 data sets with 1 trillion points in your browser. So we'll browse around a bit. This is the Rijksmuseum in Amsterdam. You can kind of see the level of detail thing with the octree I was talking about. So this is to give you a sense of the scale of the data we're working with. Down there we've got a recently released Dublin data set. So this was published by NYU pretty recently. So it's actually 1.4 billion. That should be a B. But it's relatively small compared to some of the others, but it's quite dense. It's pretty data. And we've got some stuff over in the US there. So we've got another 500 billion points over in the US. So we can go look at the Statue of Liberty in New York City, take a virtual tour of the monuments in DC. And then we will go to the Midwest next to see some of the larger statewide holdings that we've got indexed. So this is 450 or so billion points. We'll look at those later. And we'll finish up in New Zealand with a close-up of where you can see each of these points as an individual point record. You can kind of see where scan lines from how the laser ticked off each of these points, where they overlap. So it's a lot of data. I mean, we're looking in your browser at many, many terabytes of data. I'm not sure how much, but it's a lot. So visualization, yeah, we can do visualization, and we've it's visualization first, so I'm glad that we can do that. So yes, we can do that. And probably at this point, a lot of the point cloud people are saying, but so what? I mean, it's kind of cool, but people that are working with point clouds aren't doing so with the end goal being a visualization like this. So they're doing things like scientific analysis, they're doing change detection, or things like that, or they're making derivative products. Maybe you're creating rasters out of this. Who knows? There's all sorts of reasons, but it's usually not visualization. And the answer to so what is that, well, it is visualization first. That's not visualization only. And the way that these services are set up is that they ease the burden of point cloud fluffiness, like this little puppy we've got here. So by fluffiness, I mean that a single point record, like an XYZ and some of those attributes, gives you almost no information. It really tells you nothing. It could just mean that there's a point here. So you have to start aggregating this data to get anything useful out of it. Even a handful of points might tell you almost nothing, unless you aggregate it in a very specific way, at which point it starts to become unwieldy. So what we're trying to do with Greyhound is kind of ease this burden, let you get only the stuff you want at the resolution you want, and it makes a lot of things easier. So I'm going to go over some samples of what can you do with this besides visualization. So analytics. I'll go over a couple of quick analytics examples. So this is the Dublin data set. We browsed to it briefly in that video. So these are the flight lines. So they flew a bunch of flights. It's 40 or 70, I forget the number. So it's a bunch of irregularly shaped files. And how can we estimate the density? So without something like a spatial index, that would be very difficult. We have lots of irregularly shaped things. We have lots of overlap. We would probably have to download the whole set to get a really good estimation of the density. There's nothing we can do by looking at metadata, really. But with Greyhound, that's actually really easy. You can just randomly sample patches within that set and count the points and then accumulate an average density. So it's maybe a little bit of a contrived example, but it's something that you might do. And actually, I'll come back to that example later. So now we'll go to a farm in Iowa for our next example. So this is colored by intensity values. And as you zoom out, you see it's pretty to a point, and then things start to go wrong. And you might have noticed this in the video earlier, and the intensities aren't normalized properly. So we have this patchwork that just isn't visually appealing. So I'll show a quick kind of diagnosis step. So we'll do some visual quality control. So we'll color by elevation. We see there's a bunch of noise, so we'll apply one of those fancy noise filters and filter out the noise classifications. Looks much cleaner. And what you're going to see is that if you color by intensity and you blend that with the coloring of the original files in the set, is that they line up pretty well. So you can see it's kind of on a per file basis. So when you think about how you might correct this, it's pretty simple logically. Maybe we can just apply an intensity scaling per file. But this is 500 billion points. That would be very difficult to go actually fix that in the file. And then you've changed it. You've thrown out the originals. What if, I mean, that's a lossy thing because you're probably doing rounding and clipping and stuff. So how can we kind of approach this using the tools Greyhound has? And pretty simply, you can just query each file at a very low resolution, average the intensities of that file, and then we could average the averages for a kind of target intensity, and then just scale all the intensities on the client up to that target by their file average. So here's kind of what the query for that might look like. So you select each path individually. Maybe you filter the noise because you don't want to count those points because who knows what their intensities may be. You clip the resolution very low, so you're only getting a few hundred or a few thousand or however many points per file you want. And we only care about intensity, so that's all we're going to request. And so this is a 450 billion point set between those two states. And it looks much better. It's not perfect. It's a pretty naive approach. It's kind of and you see some spots are just black because they have no intensity to begin with, so you can't really scale that very well. But it's better. And so this is an approach we did in 5 minutes on almost 500 billion points, and it makes for a much nicer visualization. So there's all sorts of analytics that you might do with this kind of power. We talked about sampling and kind of visual quality control, but pretty much anything where you want to analyze large areas, but you don't necessarily need all the points. So imagine analyzing those 640 billion points of the Netherlands. Maybe you're looking for flat surfaces. You don't need all the points. That's something you can't do with the tiled scheme, but you can do with this. So there are plenty of analytical approaches. And so we talked about create and read, and the next question that probably a lot of point cloud people are asking, well, what about update? So a common workflow for point clouds ends up with the end product being more attributes for that point cloud. And yes, we can apply updates. So this is something pretty new, so so here's kind of what it looks like. You make a query and you get a bunch of points. That's simple, we talked about that. So then if you make a buffer of new attributes that have a one-to-one mapping to that query, you push that back up and the server will apply those new attributes to that point in the future. So I added this my attribute there, and there's a kind of pseudo attribute called mask, which lets you eliminate edge effects by only writing a subset of what you read. And it might look something like this. So maybe you want to run an algorithm over this lovely Autzen data set, but you can't, your algorithm is very sensitive to the number of points, so you can't run it over it all at once. So maybe you tile it and you buffer it out to eliminate edge effects, and then you do it again and again and again and again and again, and eventually you've run your algorithm over the whole set. And you didn't have to do the whole set, maybe you only cared about a part of it. So I'll do a sample here. So what if we want to classify with a ground classification algorithm Central Park in New York City? And to put Central Park in context of its data set, it's a relatively small sliver of data in a 5 billion point data set. So you can kind of see it as I zoom in and out. So this is the Poetry client. So with tiles, you're gonna make your polygon to clip. You're gonna download a bunch of large tiles. Maybe you're gonna clip them again because you need to use smaller patches or something like that. I don't know. But so we're gonna do it using Greyhound. So first I'm gonna pick some points. You see I buffered it out generously so we can see how these algorithms perform in cityscapes as well as the park area. And the first thing I did was I sampled the density, just like I talked about with Dublin. So I actually had a reason to do this. So these algorithms that I'm going to run on it are sensitive to the number of points. So I wanted to figure out, well, what's the average density? So then I can define my own tiling scheme. So this is the original tiling scheme, these big tiles, and the smaller ones are the ones that I split up. So I chunked these myself. You can see there's no correlation, they overlap and stuff, and it doesn't matter to me because that's abstracted away. So I'm going to run a ground algorithm in parallel on each of these tiles, each of them buffered out to eliminate edge effects. And here's some results. It turned out pretty well. So this first one is the progressive morphological filter. You can find that in the Poodle suite. So that's one of them. This one, I don't know what that stands for, but everybody calls it the Smurf filter. So there you go. Simple morphological. What's the R? Filter. That's not R. Okay. I see. All right. So we have perf and smurf if we go by that. And is that the eclipse? Anyway, so you can see that the algorithm ran. So we have blue spots which are ground. We have purple spots which are not. And another thing that I wrote, instead of just writing the output, I also wrote the diff. So I wrote where these algorithms disagree. So you can see here they mostly agreed. I mean, they're doing the same thing. But some of the green spots, you can see that they disagreed. And we'll zoom in on one of those. So we're in the top left of these, at the left towards the sliders there. So this is kind of where Juilliard is, the northwest side. So here's PMF. When we look closer, we can kind of see that the actual streets are a little noisy. And when we look at, especially compared to the Smurf one, we see it's cleaned up quite a bit. And something that's not as clear from comparing these, but that becomes clear when I show you the next slide, is that there's also pretty intense disagreement at the edges of buildings. And this is something that if you're writing one of these classifiers, this might be really important to you. Well, why does mine classify, why do I disagree with this other algorithm? It might also be important to you if you are an application developer and people are hosting data and you want to be able to run ground for that. Well, what do you recommend for different data? Well, you can go sample the data, run it over patches, and see what performs better with kind of a visual quality control thing. I also ran this over the infamous Autzen. So this is the defaults, which is, I think, from like TerraSolid like 15 years ago. Not very good. PMF cleans it up quite a bit, and Smurf even more. And when you look at the delta again, you see they tend to disagree on the flat areas. So they agree trees are trees, but they don't necessarily agree that ground is ground. So adding data, so we talked about that's one case of adding data. So algorithm development, classifiers, things like that, and comparisons of things like that. But you also might be doing something that is more interesting at an application level. So maybe you're a self-driving car company and you have a bunch of road data and you're going to mark the points that you think are a curb or the points that you think are a street sign or a street light, things like that. You might also be providing collaborative capability where users can annotate certain points or regions of points, and you support that at your application level. There was a case a couple years ago when the Nepal earthquake hit where they wanted seismologists to be able to collaboratively push annotations about building destruction from the point cloud data. So that's the kind of thing you could build with this type of thing. So we can create, we can read, and we can update. We actually don't have the full CRUD stack. We don't support delete, although you could append a new attribute that marks deletions and then filter on it. So we can soft delete. And back to what I said a while ago about one of the main goals of these projects throughout their whole development was that they're visualization first, but not visualization only. And the fact that we targeted visualization first led us down an interesting road that led us to kind of a pretty powerful end product. So because we had this visualization first mindset, we needed to be able to respond to user-driven access patterns. So I didn't want to write something static and have that define it because users want different things. I wanted to make the tiles for New York smaller, but maybe that wasn't small enough for somebody else's algorithm. So we wanted to, abstracting that out to be able to respond to user-driven access patterns is powerful. And because we wanted to support renderers, that was our first goal, we were driven to make things really fast so we can respond in milliseconds to these queries. There is significant future work to be done. So the appending data attributes part that I talked about, so the pushing data back, currently that's very much a prototype, so it hasn't been merged up and rolled into a release yet. We've also gotten a lot of requests for expanding the meta API. So the API for actually working with point data is fairly robust, but if you have a lot of resources, things like resource discovery, how do you know what you have and where it is? Right now that's left up to the application. And I mentioned that these products were built upon Poodle or PDL, either way. So we could do things like support arbitrary Poodle pipeline execution on the server, or do more complex filtering that Poodle has, or do anything Poodle can do, like rasterization, colorization, etc. So a more robust back-end kit there would be nice. Here are some links to projects. So most of them are pretty self-explanatory. The last two are the renderer demo pages, so you can go look at the different renderers and look at the resources we have indexed. So that long video I showed before was the Poetry client. But that's all I have, so thank you very much. Any questions?
What coordinate system are you using to maintain this data point?
So the question is, what coordinate system are we using? So we can use any coordinate system. So Entwine supports reprojection to whatever you want. For the one that I showed with the long video, those are all in WebMercator. Just because the Specly client, or Plasio there, you see at the end, that supports imagery overlay of satellite imagery on the renderer in real time. So for data sets that don't have imagery, we like WebMercator because we can easily just overlay it with satellite imagery from Mapbox and ArcGIS and stuff like that. But we tend to use WebMercator for that reason, just because we're building visual demos. But could be anything. Anyone else? Yep.
Is the octree that you guys are using in Entwine, is that kind of like a kind of a general purpose octree, or is it kind of limited or
It's pretty much a general purpose octree. So that it's got some kind of implementation detail features that allow us to be able to index things that are 700 billion points as a single set, so because that's a pretty big octree. But essentially, it is a pure octree. So
what's the biggest data set you guys have?
it's the Netherlands at 640 billion points. That's the biggest contiguous that we have. They're already working on their next, so that's AHN2. That's the name of the data set. They're currently doing AHN3 right now, so maybe in a couple years we'll have a 1.5 trillion point set for Netherlands. Actually, I think I have a tab with that. Any other questions though?
Sorry, one more.
You next. Yeah.
Sorry. The rendering in the browser, is that something that you guys implemented on your own, or are you using the library?
So the renderer in the browser, the Plasio client, I don't know if some of the point cloud people might have used Plasio a long time ago, where you could upload LAS files, or they would decompress them in the browser and show you, and it was a static renderer. That one's developed in-house, so we expanded that to be a dynamic version of that, which talks to the octree. This one is Poetry, which kind of predated us, so we hooked the back end of Poetry into Greyhound to provide this. And that was kind of one of a nice proof of concept that we're generic enough to be able to plug into anything that wants to query data. Back there?
Is there any capabilities built in or planned to allow for retrieval of large data sets for end user?
Retrieval of what? What was that?
Retrieval of files or sections of the data set by extent?
Yeah, so you can already do that via PDL, so you can retrieve a file that way and run it as an input to a Poodle pipeline. So I kind of quickly breezed over the filtering portion, but if you can pass a filter with a pseudo dimension or pseudo attribute called path, and you can select original paths from the input, and that will just download that tile. So we don't really have any client applications that expose that via like a renderer with like a click the tile and download it, but the functionality is already in the back end. Anyone else?
Last question. Going once, twice. Well.
All right, thank you.